Use the proof technique illustrated in exercise 24 to prove that if n is any positive integer that is not a perfect square, then the square root of n is irrational. Now, according to the unique factorization of integers theorem, otherwise known as the Fundamental Theorem of Arithmetic, we can use this theorem to rewrite n as a unique factorization of prime numbers. So let's write out this proof. Now, to do this proof, we're going to use the proof technique illustrated in exercise 24, which I didn't do a video on, but the idea is that we're going to do a proof by contradiction, which means we're going to assume the negation of the statement that we're trying to prove. So instead of proving that the statement is true, we're going to prove that the negation of the statement is false by drawing out a contradiction. So we're assuming that an implication is false, which means that the hypothesis is true and the conclusion is false. Also, since this statement is originally universally quantified on every positive integer n, then the negation that we'll be assuming here needs to be existentially quantified. So assume n is a positive integer that is not a perfect square, such that the square root of n is rational. So this is a negation of the conclusion, which is a component to the negation of the entire statement. So here we've assumed the negation of this statement. Now we need to draw out a contradiction somehow. The first thing we're going to use is the unique factorization of integers theorem, which says that we can rewrite this integer n as a unique product of prime numbers. So by theorem 4.4.5, there exists a positive integer k, distinct prime numbers p1, p2 all the way up to pk, and positive integers e1, e2 all the way up to ek, such that n is a product of prime numbers. And any other expression for n as a product of prime numbers is identical to this, except perhaps for the order in which the factors are written. Now you might be wondering, how did I know to use this specific theorem at this specific point in time? Well, it's because the hint here says use the proof technique illustrated in exercise 24. So this is a part of the proof technique that you need for exercise 24. The next thing we're going to do is we're going to unpack the statement, the square root of n is rational. So since the square root of n is rational, that means it's equal to a divided by b for some integer a and for some non-zero integer b. So now we can do algebra by squaring both sides of this equation, which is an aspect of the proof technique done in exercise 24. So by squaring both sides, we get n equals a squared over b squared. And then by algebra, we can bring the b squared to the left-hand side to get n times b squared equals a squared. The next trick we're going to do is we're going to substitute the prime factorization of n into this equation here. So by substitution, we have this prime factorization times b squared equals a squared. Now there's one assumption that we haven't unpacked yet, and that is that n is not a perfect square. So since n is not a perfect square, then there exists an integer I such that I is somewhere between 1 and k, such that e sub I is odd. Let's talk about why this is the case. Now, if n were to be a perfect square, then each of these exponents, e1, e2, all the way up to ek, would be even. But since n is not a perfect square, that means that at least one of these exponents has to be odd. And so that's why we're pulling out e sub I and assuming that's our odd exponent. Now, since e sub I is odd, then e sub I equals 2x plus 1 for some integer x. That's by definition. So now we can rewrite this equation and derive our contradiction. The contradiction comes from counting the number of factors of p sub I. Now keep in mind that p sub I is one of these prime factors from p sub 1 to p sub k, and e sub I, which is equal to 2x plus 1, means that there's an odd number of factors for p sub I. So what we're going to do is we're going to count the number of factors of p sub I for all three of these objects here and derive a contradiction. So from the prime factorization of n, we have an odd number of factors of p sub I. Now the number b might be divisible by p sub I. However, because b is squared, then in b squared, there's an even number of factors of p sub I. Since regardless of whether there are an even or odd number of prime factors p sub I in the prime factorization of b, when we square the number b, then that means that there is an even number of every prime factor. The same can be said about a squared. Regardless of whether or not there's an even or odd number of factors of p sub I within a, when we square a, then there will be an even number of factors of p sub I after we square a. So there's a contradiction here, but as mathematicians, it's our job to draw out those contradictions for the reader. So here's what we're going to do. We're going to count the number of factors of p sub I on the left-hand side of this equation, and then we're going to count the number of even factors on the right-hand side of the equation and derive a contradiction. From the purple section, we have an odd number of factors of p sub I, and then we add on the number of factors of p sub I from b squared, which is even. So that means if we have an odd number of factors of p sub I plus an even number of factors of p sub I, well, as a result, we get an even number of factors of p sub I. And this is where the contradiction comes from. We have an odd number of factors of p sub I plus an even number of factors of p sub I equals an even number of factors of p sub I. That's not possible. This is a contradiction. So now we have to ask the question, what did we contradict? Well, everything here is valid. We didn't make any mistakes throughout this entire proof, and so that must mean that our original assumption here is false. Since everything past this assumption is valid and the conclusion is a contradiction, then that must mean that this assumption is false. But if this assumption is false, then that means the original statement is true, since the original statement is just a negation of the assumption. And so that's how this proof by contradiction works. Thanks everyone, and I'll see you in the next video.